Morning, guys. Sorry I'm not there today now. I'm on training, but I don't really want to miss class, so we are going to keep going. Mr. O'Rourke told me that you did the problems yesterday, these ones here. So we had done a couple of F equals MAs, and I suppose the main one was this one here. I wanted you to understand the idea that if there is a resultant force, so a combined force, an overall force acting on a mass, that it will accelerate. Okay, so sorry, I lost it. So in this one here, in A, is there a combined force acting? You have a 10 Newton force on the left and a 34 Newton force on the right. So that means overall we have a force to the right of 24 newtons. So we do have a resultant force. So if we do then F equals ma, the force is 24, the mass is 8, and we need to figure out the acceleration. So we're trying to isolate the a. We divide by the 8 to isolate the a, and divide by the 8 on this side. And we know that it's 3 meters per second squared. Okay, and acceleration is a vector, and the acceleration will act in the same direction of the force. So if you take this 8 kilos up here, it is going to overall move in that direction to the right, and it's going to move to the right with an acceleration of 3 meters per second squared, because the forces in this case, the fact that there is a resultant force means we would call those forces unbalanced. Okay, for obvious reasons, they are not balanced, they are different on either side. Okay, whereas if you look at this one here, there you have 150 Newton force to the left and 150 Newton force to the right. So overall, the resultant force is 0 newtons. Okay, so when we do F equals ma, we get 0 is 8 times a. We want to isolate the a, so we divide by 8, divide by 8, so the acceleration is 0. Okay, which is probably quite obvious. The fact that it has no resultant force means it has no acceleration, but I want you to think more about what acceleration means. I'm sure Mr. O'Rourke went through this, but what does acceleration mean? Acceleration means we have a varying velocity. So we have something that is either speeding up slowing down or changing direction. Okay, so if we have no acceleration, then that means we do not have a varying velocity. So if we have 0 acceleration, then we have we're talking about a constant velocity, not a varying velocity. Okay, so again, think about what that means. Okay, is that 8 kilogram mass moving or not moving? Okay, so again, I'm sure you went through this yesterday, but I just want to be clear. It could be either. Okay, so this 8 kilogram mass, the fact that it has no resultant force and as a result no acceleration, that means it has a constant velocity. That constant velocity might be 0, which means this object is not moving. Okay, but it could be moving, just not accelerating. Okay, so if you have an object that's moving, so like maybe in the beginning, I'll take this off in a second, but maybe in the beginning this force here was bigger. So it was accelerating to the right, accelerating to the right, accelerating to the right. And then as the speed picked up, this force, maybe it's friction, maybe it's air resistance, but that force kind of got bigger and bigger and bigger to the point where they were balanced. Okay, so originally, now I'm hypothesizing here, but originally the force on the right was bigger, so that object was moving or accelerating in the right direction. And then as it picked up speed, the force to the left, the one over here, got bigger and bigger and bigger to the point where they became balanced. Okay, so if the object was already moving and then the forces became balanced, what happens then is it will continue moving, it just won't accelerate anymore. It will continue moving at a constant velocity. Okay, so that's this scenario down here. Okay, but then the other scenario is if you have this 8 kilo object sitting on the ground and I pick up a rope on the right hand side and someone else picks up a rope on the left hand side and we both pull with 150 newtons, that is not going to move anywhere because the forces are balanced. Okay, so just to be clear that there's two scenarios there and you do need to be able to understand both. Okay, right, so we're going to look at momentum. The reason I kind of went back on that just to make sure we're very clear is because we're going to talk about it again. So momentum. Momentum's kind of a weird one to explain, but like I always think of momentum. Now this is not a physics definition, this is a very kind of flippant definition, but I always think of momentum as how hard it is to stop something. Okay, so if something has a large momentum, then it's really, really hard to stop. If something has a small momentum, then it's not that hard to stop. Okay, momentum is, I'm going to move over to the side here just a little bit. Something's momentum, so how hard something is to stop is dependent on two things. Okay? The first thing that it's dependent on is mass. So, generally speaking, big, heavy objects are harder to stop. Okay, and the second thing they're dependent on is velocity. So fast objects are harder to stop. Yeah? So momentum, from a physics point of view, is the product of mass and velocity. Okay, and hopefully we remember, but I'll just say it just in case. Product means multiply. Okay, so momentum is the product of mass and velocity. So you're going to take whatever the object's mass is, and you're going to multiply it by its velocity. And that's how you figure out its momentum. So it doesn't have to have a big mass and a big velocity to have a large momentum. It kind of just has to have one. So kind of a good example, I think, of this would be sort of comparing like a bullet versus double-decker bus. Now, both of these, I hope you agree, are pretty difficult to stop. It's incredibly difficult to stop a bullet. You need, a substantial amount of metal, I suppose, and then obviously it depends on the bullet too. But like even those bulletproof vests and things like that, like the Kevlar that's in that, that's it does find it quite hard to stop it, and even then, the force that it takes to stop the bullet, the person will still be covered in bruises and things like that. So bullets are very, very hard to stop, and as are double-decker buses. If you watch a double-decker bus even trying to start up at like traffic lights, or like you'll notice this with like big lorries, just like that, anything like that, like those big road vehicles with like large mass, they're really, really slow to get started. And then also if they're coming up to traffic lights, they take forever to slow back down again. So their large mass kind of gives them a really big momentum. So here's an example. I'm sure you've got this now at this stage, but here's an example of a bullet which has, generally speaking, a very small mass. Normally like grams, like maybe 10-12 grams kind of mass, but it has a really high velocity. So a bullet's momentum, and we've agreed that it has a high, well, I don't know if you've agreed, I'm not there, but let's hope you've agreed. So it has a high velocity, it has a high momentum because of its high velocity. And then a double-decker bus has a large mass, relative to the bullet, it has a pretty slow velocity. Like I don't know what I'd say, it's completely slow. Like, double-decker buses will drive up at 60, 70, 80 kilometers per hour, but relative to the bullet, it's quite slow. So in this example, the double-decker bus is getting its momentum from its large mass. Okay, so it doesn't necessarily need to have both. Now, if it has both, if you take the double-decker bus and put it on the M50 going at 120 kilometers per hour, that has a huge momentum. Okay, so that's momentum. Okay, generally speaking, the definition is just the formula, so it's just this here. The product of mass and velocity. So a couple of other things about momentum. There's a symbol for it. So this is here. So the symbol for momentum is P. Momentum is a vector. Okay, the fact that it's mass times velocity and velocity is a vector, that means it's going to be a vector. So if you have, let's go back to my double-decker bus. So here's my double-decker bus. It's fabulous. If I have a double-decker bus and it's travelling down the road with a velocity of 40 kilometers per hour, then its momentum is also going to be in that direction. Okay, so that makes it a vector. And now the unit for momentum. So I'll do the unit in here. So momentum is mass multiplied by velocity. Yeah. The unit for mass is kilogram. The unit for velocity is meters per second. And that's the unit for momentum. It's kilogram meter per second. Okay, it's a compound unit, it doesn't get changed to anything, it's literally just the two of them stuck together. So kilogram meters per second. Alright, so we'll have a quick look at problem 7. So we have a bus of mass 5,000 kilograms moving east at 15 meters per second, find its momentum. So we write down the formula. Momentum is mass times velocity. The mass, we will sub in the 5,000. It is in kilograms, and kilograms is standard unit, so we can leave that alone. Velocity is 15. Again, 15 is in meters per second, so we can leave that alone. We multiply 5,000 by 15 to get 75,000, and then the units are kilogram meters per second. And the fact that we know momentum is a vector, we're going to have to look and see if there was a direction, and if there was, it needs to be included. And there was. So we add the direction on. Okay. So they're going through the units there, which I've done already. I don't think there's any here. We need to do more. Sorry, give me a second. Okay, no, they're kind of connected. Okay, I'm just going to talk through the Newton's laws. So I don't know if you've heard of Newton's three laws, but they're pretty famous because they kind of govern a lot of what we know about forces in motion. So they're literally called the laws of motion, and they pretty much govern a lot of what we know. So we will come back to momentum because we do a lot more work on momentum, but it has to, the reason we do a little intro there is just purely because it's mentioned in the laws. So the first law states that every body will remain in a state of rest or travelling with a constant velocity unless an unbalanced force acts on it. That is literally what I discussed earlier. You know the example with the 8 kilogram mass and the 150 newtons on this side and the 150 newtons on this side? That is literally what this is about. Okay, so Newton's first law of motion states that every body will remain in a state of rest or travelling at a constant velocity unless an unbalanced force acts on it. Okay, so if you have a balanced force, this object will either be in a state of rest or travelling with a constant velocity. Okay, which is exactly what I explained earlier on when I went through that question. So there are two options for this 8 kilo with the balanced force. Either the balanced force is acting on it when it's stationary, in which case it won't move, or the balanced force is acting on it when it's already moving, in which case it will keep moving, but it will move with no acceleration, which means a constant velocity. Okay, and the only way to break this, the only way to stop it being either at rest or traveling at a constant velocity is if you introduce an unbalanced force. Okay, so if this is sitting flat on the ground and I'm pulling at this side and someone else is pulling at this side and random person number 3 arrives in and starts pulling with 100 newtons, that's now unbalanced. Will it now move with a constant velocity, or will it stay at rest? No, it won't. Okay, that's going to get it moving. Okay? So that's what that one is about. The second one relates to momentum, which obviously we've just discussed. So it states that when you have an unbalanced force on a body, the rate of change of the body's momentum is directly proportional to the force and takes place in the direction of the force. So the other example we did, been easier to do this, but anyway, so here's the other example we did earlier. Okay, so in this situation we had an unbalanced force. We had a here we had a resultant force because it was unbalanced. Yeah, so overall we did have an acceleration. We did have an unbalanced force, and as a result we had an acceleration. Okay, so the fact that this object is moving to the right with 3 meters per second squared, yeah, that means we have a varying or changing velocity. Yeah, so the velocity is changing. Okay, so what we have is we have a mass, 8 kilos, traveling at a particular velocity, and then maybe 2 seconds later we have the same mass traveling at a different velocity because it's getting faster, and then a couple of seconds later we have the same mass traveling at a different velocity. So the velocity is changing, which means the momentum is changing, because remember, momentum is a combination of mass and velocity. So the mass isn't changing, it's just the 8 kilos, but the velocity is changing. Okay, the fact that this object is accelerating, that means the velocity is changing. If the velocity is changing, then the momentum is changing. Okay, so changing varying velocity means the momentum is changing. Okay, and what this law says is that when the force is unbalanced, so we know that when we have an unbalanced force, the object is accelerating. Okay, like in the example I've just attached. So when an unbalanced force acts on a body, the rate of change of the body's momentum, okay, so the momentum is changing, yeah, and when it says rate of, this bit here, that just refers to time. Okay, so what that means is that at 1 second the momentum will have a value, but then 2 seconds later it will have a different value. It's changing with time. Okay, they're saying that is directly proportional. Now, we came across directly proportional before, remember, with force and acceleration. So we were saying that if you double the force, you double the acceleration. If you triple the force, you triple the acceleration, and so on. So the unbalanced force acts on a body, the rate of change in momentum is directly proportional to the force. Okay, which I think hopefully makes sense. So what they're saying here is that the bigger this resultant force is, the bigger this acceleration is, which we know, and as a result, the bigger the momentum change is. Okay, because if it's accelerating more, that means its velocity is picking up quicker, and the fact that momentum is related to velocity means that's picking up quicker as well. So the force is proportional to how quickly the momentum changes. Okay, that's what Newton's second law says. Now I'm going to put a big star here. Remember we did proofs earlier? We did them. I remember making a folder for them. Where are they? Here. So we did the derivations. Remember these? So I have it there. There is a proof connected with Newton's second law. Okay? I'm not going to do it here. I'm going to do it in class with you tomorrow. Okay? And then the last one is one you may have heard of. So Newton's third law states that if body A exerts a force on body B, then body B exerts an equal but opposite force on body A. Okay, this is generally how people know it, if you've heard it before. Every action has an equal and opposite reaction. I think the best example of this is like if you have a balloon. So if you have a balloon, not a balloon, a balloon, and it's full of air. If you have a balloon and it's full of air, And this is like you're holding this down here, and then you let go of holding it, the air will shoot out the back, okay? And the force of the air shooting out the back, I've just said it, that is a force. It will exert a force. Like if you put your hand on it, you'd be able to feel the force against your hand. So the air exerts a force in that direction that I've just drawn. And where will the balloon go? The balloon will shoot off in the opposite direction of the air. Now, generally, it's very erratic because as the air comes out, because the balloon is so elastic, it kind of moves around. So the air kind of shoots out as a stream, but it keeps changing direction. But if you put, I've done this before, if you put like a straw on top and feed a string through the straw, do you know what I mean? And like tie it up on the ceiling or something, you can get it to go in a perfect straight line. So the air coming out the back will cause an equal but opposite force on the balloon moving forward. So that is an example of Newton's third law, where the fact that the air was released from the back and that exerted a force in that direction, that caused the balloon to move in the opposite direction. So every action, here's your action, has an equal and opposite reaction. There's your reaction. Okay, that's Newton's three laws. And like I said, I'm going to do the proof tomorrow of Newton's second law. That's down there. I want you to do a couple of questions. So we're going to do, see right there, 9, 10 and 11. I'll put them into the journal and on Schoology. But yeah, do 9, 10, 11 and see how you get on. Okay.